So yesterday we went through one example talking about how to calculate moment of inertia. The basic idea of moment of inertia is that we have an object rotating around an axis, okay, and we need to know if we have a torque applied to this specific object, how are we going to obtain its angular velocity and those kind of things when you are dealing with the concept in dynamics. So when we try to calculate this part, we define moment of inertia based on if I have Ix, which is rotating around x-axis, the distance over here is y. If we are talking about the area moment of inertia, then Ix equals to y squared multiplied by 8. If we have this one rotated around y-axis, then Iy equals to n squared 8. So that's a basic definition of moments of inertia. If you need to find real moments of inertia, you simply replace A with mass. Then you get everything. But this is only for particle objects. Most of the time, we're not dealing with particles. Instead, we deal with objects. So when we have objects, there are two ways to do that. One is using integration. So we integrate everything based on the area in pieces, or if you define everything in discrete type, then Ix is going to be yi squared delta ai iy equals to xi squared ai as well. So this is going to be the definition of what we have for a moment of inertia rotated about a specific axis. If you need to calculate for the moment of inertia around about the axis, the process is going to be similar. However, if we have those two things, but those are not something we're looking for, we are actually looking for the moment of inertia rotated around its origin. In this case, what we're going to do, because we know the distance between origin and the object is going to be r, and by triangular relationship, we know r squared equals to I squared, x squared plus y squared, which means the moment of inertia rotated around O becomes Ix plus Iy, which is a definition of r squared a dA, and r squared equals to x squared plus y squared, so which yields is actually a combination of those two terms. This can be useful because a lot of time when you are trying to find the formulas, you only given Ix and Iy. You never given the information of J. So, however, if you can just get the formula for Ix and Iy, you should be able to get everything based on what you calculated. Okay, so that's the idea. And yesterday we went through one example, which is triangular shape, and we try to find the moment of inertia with respect to its base. Everybody understand what we were talking about yesterday? Okay. So yesterday we were talking about an object like this. So when you have this object, we just integrate from the bottom, and based on this the configuration, we know Ix equals to 1 over 12 dh cubic. My b is here, my h is here. So you should be able to get the information like this. However, we don't want to do the integration in the test for this kind of basic stuff. If I need you guys to give me the information based on integration, it's not going to be that simple. So those things is those number you can actually look up from the table in your textbook. I think that's in your back of your textbook. So you can just find out the information, but there are something you would need to know before you do the calculation, because clearly the moment of inertia around here is totally different from the rotation around here, right? So let's say I have a triangle over here. Everybody know where is G or center of gravity is located, right? It's going to be in the middle. Okay. So when you have a table like this, normally it will give you two types of moments of inertia. One is around x-axis and y-axis. That sometimes we are more interested. So if this is going to be the case, Ix over here, let's define the dimension over here. Over here this is B. Over here this is H. Okay, let's define the center of gravity over here is G. So when you take your table, you're going to find you actually have 1, 2, 3, 4, 5 properties. The first one you're going to find is Ix, which is about this axis over here. If you do the integration, you're going to find nothing fancy. If you do the integration, I can show you how to do the integration now. The integration is Ix equals to y squared 8 based on the definition over here. Okay, so when you're doing this, this is my dy, and obviously the distance is going to be y, right? So when you do the integration, you're actually from 0 to h, because I'm integrating in terms of h, and my area, then y squared multiplied by my area. What is my area? It's going to be b dy. Everybody with me? This is b, based on the definition over here. So b in this case is a constant. So I can just move b out of this integration. Within this integration, it's going to be y squared dy, or So if you can get, which is something we have over here. Everybody understand what I'm talking about? Is that clear? It's just, I'm not doing anything special, I'm just following the definition given in this chapter and trying to find out the moment of inertia of a rectangle about x-axis. And you're just using the integration. Okay, so clearly, this is what? It's bottom. The length of the bottom. This is the height. So if you try to find my y, it's similar. This is your bottom because now I'm rotating around y-axis. So this is your bottom. This is your height. Okay, this is just for rectangle. But when we are calculating the moment of inertia, can we always guarantee it's always around x-axis or y-axis? I can tell you most likely it's not going to be the case. Most likely we are interested in the gravity center. Okay, so when you look read the table in your textbook, I think it defines as x prime, y prime. So when you use x prime and y prime, you're going to find ix prime equals to 1/12 p h cubic. I1 prime equals to d cubic h. Okay? You need to understand the moment of inertia is a property which is related to its position. If your position changes, then the moment of inertia is going to be changed as well. Because that's the definition over here. Everybody understand what I'm talking about? That's by definition. So it means that if the camera is my axis, I start to rotate my iPhone over here and rotate it in this distance. Is this going to be the same if I rotate? Is the moment of inertia is going to be the same if I move my iPhone over here? It's not. Which one is going to be larger? Move to this location. So clearly, rotated about its center of gravity in this direction and in this direction is going to be smaller than the moment of inertia rotated around this axis and this axis. Okay, be sure which one you're talking about. And the other thing is, now I'm only talking about the moment of inertia rotated about two perpendicular axes. A lot of time we don't care about that as well. We care about the moment of inertia around this thing itself. What it means that is Ig equals to this one, which means I need to combine this one and this one together because I try to find the moment of inertia rotated about its center, about its gravity center, which is G. So in that case, it should be Ix prime plus I1 prime, which is 1/12 bh d squared plus h squared. Yes.
Why does it go from 1/3 bh cubed to?
That's that you need to do the integration to find out because okay. You understand what I'm doing over here?
Yeah.
This is about x-axis.
Okay.
This one is about x-axis. Because a lot of time, sometimes you might be interested in, okay, I define an axis over here.
Okay.
What is its moment of inertia? Then you do that. If you are interested in this axis, you do the integration. But if you use this one, you always need to do integration. A lot of time when you are given the center, the moment of inertia is about its gravity center. So if you are given those kind of things, it's rotated. Your gravity center needs to be defined first. If you don't know where is your gravity center, you need to find it out before you move on. If you don't do that, the rest of your calculation is not going to be correct. Okay? So most of the time, those are given, those are not. So when those are given, it's about this axis and this axis. So that is something based on what we're calculating over here, but in different ways. Does that make sense? Yes.
So are we saying that I sub x prime and iy prime are integrals of ix and iy, right?
It's based on something I'm going to explain later.
Okay.
But yes.
Okay, so right now we're just yeah.
Now I just start from beginning because we used to start everything from one stuff. That is how we did this, how I do this part and how I proceed the example yesterday. We always start from one end, not starting from the center of gravity because essentially you need to integrate for both sides. It's actually not for both sides, it's actually you just change that with this one, you're going to find it's going to be 1/12. Okay, but sometimes you guys just don't like negative to positive. You guys prefer to have 0 to some end. So, okay, anyway, the point over here is when you read your textbook and you try to find out your moment of inertia, what important is you need to know what kind of moment of inertia you're looking at. Are you looking at the moment of inertia rotated about a specific axis? Most likely it's going to be at the bottom or on the side. Or it is actually rotated about its center of gravity. Those are the things you need to understand in the very beginning. Is that clear? Everybody understand what I'm trying to say? Okay. So again, in your notes, in your textbook, you're going to find a lot of numbers or a lot of formulas you can use for different kind of geometry shapes that you can look up for moments of inertia. Okay. You want me to go through how to integrate from negative side to positive side? It's actually the same procedure over here, but you're going to find the number becomes 1/12 instead of 1/3. Okay. However, we don't. Yes.
You keep telling us to look up the chart. Are you going to provide the chart, or do we need to memorize the chart?
I'll give you some. I'll give you the chart in the final. Yes, I'll give you. I will give you the chart, but in other courses, those things are very common. Seriously. In particular, if you need to take dynamics, these are something. Some of those you need to remember. In particular, those two. I think you also need to remember triangular, but
so
you don't need to worry about that this class. Yes.
The ones in the book are given around about the center of gravity, not the axis.
That again?
I mean,
some of those I don't remember what are written over there because there are about 8 or 10 shapes over there, right? Some are given all of them. Some are given only this part. Am I right? Some are giving you a lot of numbers.
I think they're all just given about the center of gravity.
Yeah. Yeah, most likely it's just giving you the center of gravity, not giving you those things.
Yeah.
So that is something you need to be careful. Okay. I think in the book of Bill Johnston, Johnston, giving you everything. In Hitler's book, giving you only this part, maybe this one, but I'm not pretty sure. So depending on which book you're using, it's going to be a little bit different. Okay. don't worry. But personally, I feel the book you're using now is better than the other book I just mentioned. Much better. Okay. Now, based on what I introduced on the other side of the blackboard, we know that if you try to find the moments of inertia, you can use integration to find out almost everything you want to, as long as the mathematical representation is given, right? However, do you really want to do the calculation all the time, in particular integration? Probably not, because integration normally means it's a problem, and the more calculation you do, the more mistake you might make, right? So instead of doing that, I'm going to talk about parallel axis theorem. For instance, I've given you the moment of inertia about its gravity center. Without doing the integration again, can I find the moments of inertia about this axis? Yes, we do. We can use parallel axis theorem. So what it means is that if I have an object, and obviously this is my gravity center over here, and let's name this one x original. Okay, so I'm going to give you a property which is moments of inertia about this axis. So I'm giving you I x original that's by definition, right? Nothing fancy, just by definition. I know it's going to be. We must use this rule. Then I define this one as my ix bar. Okay. Now I'm telling you I'm no longer interested in rotating about this axis. I actually move my rotational axis to here. So let's define this one as no, I'm telling you that I'm still giving you something which is I move the distance which is d. So can you tell me what is the moment of inertia rotated about the new axis? We can actually do that, which is J. The new moment of inertia is the original one, Ix bar given over here. If I'm giving you the area is A, then it's actually d squared A. If you don't do this over here, what is this part telling you? It's a moment of inertia by definition. But when we consider this part, it's a point area, right? We just represent everything as a point. Okay, but this time, where is this point located? At its gravity center or its central, right? So if you know its original moment of inertia around its centroid, then if you move the axis certain distance away, you just keep your original moment of inertia about its gravity center, about its centroid, then plus the distance you moved squared multiplied by the area or mass or whatever you want to calculate for the property, then that's your new moments of inertia. Okay. Is that straightforward? Everybody understand what I'm talking about? You can actually prove this. Well, I can do that, but based on my experience, you guys don't like proof. Alright. I can prove that to you. It's actually when we do the moment of inertia, what do we do? That's the definition, right? So we do have the same thing. Something like this. Okay. Then I just expand this part to here. That becomes a y squared a plus a b squared a plus 2y b squared a plus 2b a y yeah. I'm not doing anything. I'm just multiply the dA from here into individual terms, then expand everything into this equation. Okay, so what is this defined? The moment of inertia about its gravity, about its centroid. So this becomes my I x. D is a constant. So if you integrate everything together, it becomes A. Okay. Now this term over here, we are integrating about both sides. So you integrate from negative side to positive side. Since it's symmetric, so this one, when you integrate about y, it must equals to 0. So this term becomes 0. So what do I get? I get Ix squared, which is original moment of inertia about its centroid, and the combination with the distance squared multiplied by its area. So by using this formula, we prove that if you know your moment of inertia about its centroid, and you move this thing certain distance away, then we can actually obtain the new moment of inertia based on parallel access theorem using this formula. Yes. Is that clear? Everybody understand what I'm talking about? So we're going to use this formula to calculate or this as an example. But think about it. Make sure it makes sense to you and that you understand what I'm talking about. Here, for the rectangular area shown, calculate the moment of inertia about the centroidal axis, which is S bar and Y bar, and the centroid polar moment of inertia, and the moment of inertia of the area about X axis. So I need to calculate the moment of inertia using those two formulas first. Then I'll find the polar moment of inertia, which is this one, or I use J in the beginning. Then I would need to find the moment of inertia about x-axis, which should be using this one, but I'm going to calculate using a parallel axis theorem. Okay, so I'm given a rectangle. There are a few things I need to find. A, Ix, Iy, B, I need to find J, C, I will need to find Ix over here. So for the first part A, it's going to be straightforward. If you have the table, you just find those two formulas. In this case, what is your B? 3 or 4? That is something you need to identify. In this case, B is the bottom. What is your B? 3, right? What is your edge? 4. So just plug in the number. You're going to get, be sure you put the unit correctly. It's going to be fourth order instead of square or cubic. Okay? Iy, it is the same. We just change the cubic term from h to b, and it's going to be, which give me 9. So far, any question? Okay. B is going to be J, which is Ix plus Iy. What do I have? Just add this one together with this one. You get 25 each fourth order. That is something we have for the polar moment of inertia for a rectangle. So far, it's not so, there is nothing difficult, right? I'm just using the formula. Now, see, if I use parallel axis theorem, Ix is something given. Before you do the calculation over here, do I know? This is the formula that you're going to adopt to calculate for the moment of inertia about x-axis. If you do that, over here I get 16, which is its original moment of inertia about its centroid. And over here, what is my D? 2 squared. What is my A? 12. So if you add everything together, it becomes what? 1248 becomes 64. Does that make sense to everybody? If you calculate from here, it should be 1/3 multiplied by something like this. If you do the calculation over here, you're going to find they're actually identical. Okay, So you can calculate those kind of things in both ways, but they must be the same result. If you find out your number are different from both calculations, then you're making something wrong. They must be identical. Is that clear? Everybody understand what I'm talking about? Am I going too fast, or this is okay to everybody? Okay. I don't get a lot of response.
Where's P in the font?
Where is P?
Oh, never mind, I see. Yeah.
Okay, and the next thing I'm going to talk about is radius of gyration. So we talked about the moment of inertia. We talked about the parallel axis theorem. Now we need to discuss a little bit about radius of gyration, because we know how to calculate the moment of inertia, but a lot of time if you have multiple objects combined together, or this is actually move around everywhere, we need to know when this condenses to a single point, what is the effective radius between the centroid and the axis we're interested in. So the definition of radius of a gyration is if we have something like this, and we find out the moment of inertia of its radius, then we would like to know what is the distance. So most likely, we're going to have our inertia J. That is by definition d squared A, right? So this is the effective radius. So what we're going to do is d equals to J over A. If you find out the Ix in this term, it's going to be y squared A, then y equals to Ix A. Because everything over here is the term over here and over here, well, they are definitions, so you cannot change its definition. And by definition, we calculate for the moment of inertia, all based on a single point, or a point mass, or a point area, you name it. So when we assume everything is just a single point, what is the radius between the interested point? Sometimes it's origin, sometimes it's specific axis like x or y. Then how are we going to find, if you just given a simple number, area and the radius, what is the radius you're going to be given? That is how we use radius of gyration. Okay, so in short, we try to simplify everything into only two values, area and distance. Is that clear? Okay. So another example. After this example, I'll give you guys an example. for a semicircular area shown, calculate its radius of gyration with respect to the x-axis. So this is the axis that I'm interested in. Again, just like what we did in most of the problems, we need to define what are given and what we need to find. We are given semi-circular shape. In this case, R equals to 40 millimeter and D equals to 28 millimeter. Do I want to use D? I want to find the radius of gyration of this thing about x-axis. Okay? So let's go. So obviously, I'm not interested in doing the calculation or the integration. So I'm going to look up the table, finding out the moment of inertia of this semicircular directly. If you do that, you're going to find Ix is formula. So if you do the calculation, it's going to be 2.81. I convert everything in terms of meter. So this is something I have, but can anybody tell me where this what is the meaning of this moment of inertia? Is this one about x-axis, or about its bottom, or about its gravity center, or centroid? When you look at the table in your textbook, that's a challenge. Centroid. So it's central. It's going to be here. Okay. So when you have this property, it's talking about is rotating about this arc. Obviously, that is not something we're looking for. We're actually looking for this thing rotated about here. Okay, so the next thing we need to do is to finding out the moment of inertia about this axis. But before we do that, another thing we do need to know is what is the distance over here. Let's say this one is yg. Okay, so yg is going to be, I think I talked about this in chapter 9. This is something you guys do need to remember. Okay. So if you do the calculation, you're going to find this is 0.017 meter. Okay, it's a formula. Now, I would need to find Ix based on parallel axis 0. What do I have over here? Ix is d squared a. Right? This is another definition we need for the formula. Not definition, this is another derivation. So I get my Ix from here. What is my d? In this case, the d is between the centroid and the axis you are interested in. So in this case, my d is going to be 28 millimeter plus 17 millimeter over here, which gives me that's a D over here. Everybody understand which portion I'm talking about? And A is straightforward. It's going to be 1/10 pi r squared, which is going to give me this. So I got my A, I got my D, I just plug, and I have Ix bar, so I just plug this number, and this number back into this equation, then I should get everything, which makes my Ix equals 5.37 multiplied by 10 to the power of -4 meter fourth order. Okay, I'm not doing anything special. I'm just finding out all the properties and combine everything together, get my new moment of inertia about x's. Okay. But that is not something I'm looking for. I'm actually looking for the radius of gyration. So when I'm looking for the radius of gyration, Rx is going to be Ix. A is something we know over here. Ix is given over here. So if you do that, you're going to get the radius of gyration is like that. Meaning that if you want to define everything over here, you should define that area at this position with this distance rotated about x-axis when you are using this moment of inertia. Is that clear? Everybody understand what I'm talking about? You sure? I prepared something for you guys today, so you better understand what I'm talking about. If you guys don't have any questions, let's take a 5-minute break. Yes?
First IX.
This is by definition. You look up the table. This is from the table. Okay. Radius of gyration. So, in most cases, you are not going to encounter a mechanical component, which is just typical geometry shape. It's going to be a combination of a lot of things. For instance, something like this. And if I'm asking you to give me the moment of inertia of this thing, what are you going to do? I am given mechanical component. We need to find Ix, because in this case I'm asking you to find out the moment of inertia about x-axis. So clearly this is not a shape you can represent using mathematical function, right? So we would like to decouple this thing into different parts, then combine them together to get our moments of inertia. So how many pieces you think is adequate? It's just like what we did in chapter 9. You just combine, you just separate everything in terms, then just do the calculation. You should be able to find everything. Okay, so the first thing we need to identify is how many pieces you want to decouple this piece. 1, 2, 3, 4, 5, 6, 7, or 8, or 9.
4.
5. Can we use a little bit less?
4.
4.
You do 2.
Well, it's still too many. I would like to use 2 is too few. But the best you can do is 3. Okay. You can certainly you can do all kinds of things. You can say, okay, decouple this part, and you have a square and this part, and you have another square over here. Get rid of this triangle over here, and this becomes 1, 2, 3, and 4, right? But can we just use this big rectangle over here?
No.
Okay. And get rid of this part, then get rid of this part. Then how many pieces I'm using? Oh, I know you have different opinions, and you have problem with me. We can talk about that later. No, I'm just kidding. Okay, so we can use this big chunk over here, get rid of this triangle, and get rid of this semicircle, and we should be able to find everything. However, just like what we did in chapter 9, before you do that, I would suggest you guys build a table, so everything will be a lot easier when you try to combine everything together. Does that make sense? So, keep in mind what we need to calculate for when we try to calculate for moment of inertia, what we need to do. But the first thing I would like to do is to decouple this into 3 pieces. If I decouple this one, this is going to be 700 millimeter. Over here, this is 1000 millimeter. Okay, and the second piece I would like to do is the triangle over here. This is going to be 300 over here, and 400 over here. Another one is a semicircle, which radius is 200 millimeter. 100 millimeter. I will name this one A1, A2, A3. Okay? Table. 1, 2, 3. Based on the formula over here, what do I need to have? I need to have the moment of inertia about its centroid. I need to know the distance between the centroid and x-axis. I also need to know the area. So we need to have 3 information: A, Y, I, X. Does that make sense to everybody? Okay, so let's start from A1. So A1 is going to be 1 meter multiplied by 0.7 meter. That is going to be 0.7 meter squared. So I just put 0.7 over here. Keep in mind, you need to put a unit over here. Okay. So what is my Y? Related to 0.35, right? What is my moment of inertia around its radius? about its centroid, we just do I1 E is 1, H is 0.7 cubic, so I have okay. A2 is going to be 1 half, 0.3, 0.4, that is 0.06. However, is this an addition part or this is a subtraction part? Subtract part. So keep in mind when it's cut out part, you need to add another. You need to add a negative sign in front of it. So we have negative 0.06 over here, and the distance over here. You guys still remember how we calculate for the position of gravity, right? It's going to be 1/3 from the bottom. In this case, what I mentioned that is about x-axis, so I would need to know the position here in this direction. So it's 1/3 from the bottom, which means it's going to be 0.1 meter below the upper edge of this triangle, of this rectangle. So it's actually 0.6 meter away from x-axis. Does that make sense to everybody? So I just put I2 is going to be this is the cutoff point. Remember to add another negative sign in front of it. So you're going to have okay. For the area of this thing, the semicircle, it's going to be 1/2 pi r squared negative, because it's a cutout part as well. So if you do that, it's going to be something over here. Then I need to find y. Based on the definition, it's 4r over 3 pi. Do I need to shift this number to any other location, or I can just use that one? I can just use that one, right? Because now this is at the bottom, so over here is calculated from the formula, correct? So if you do the calculation, you're going to find this one is what is it? Well, for some reason, I think my notes always use the negative 0.1098 as a formula. I need to figure out what's going on here. I'll let you know why I'm using 0.1098, which is something your question. Let's check. Here. Okay, I'll let you know what's going on, why I'm using this number, because I didn't mark it anyway. I'll let you know why I'm using this number instead of that number next time. Okay. Okay, so if you use the formula, try to find out the moment of inertia. The valve is gravity center. Use this formula. Well, it's different from what you have in your textbook. I'll let you know why it's that next time. So if you do that, you actually get so put it here. Then we have everything we need to calculate for the moment of inertia related to x-axis. Which formula are we going to use? We are having if this is a single piece, but this time how many pieces are we talking about here? 3. So we need to add a summation sign in front of it. Okay, we know this thing based on the table. We know the distance based on the table. We know the area based on the table. So we can just put everything together. Total weight is going to be 9 terms, so it's going to be a long calculation. Make sure you won't put the wrong number in your equation. But if you do that, you're going to find this is the moment of inertia when we combine everything together. Yes.
I noticed right when you wrote the inertia about x, inside your parentheses where you have the y squared a, you slipped a negative in there real quick.
Oh, you mean
Or is that just
this one?
Yeah, where it says y squared a,
squared A.
you put that little chalk line, looks like a negative in there. Did you do that on purpose, or is that just someone
No,
seeing
that's
it?
the dot for the eye.
This is
Okay.
this is the
Okay,
I.
yeah, okay. I got it.
Okay, sorry for that. Okay, so that is something we have over here, as it's a moment of inertia. If we try to find the radius of gyration, what I'm going to do? I'm going to have my r x equals to my x. Let's come over here. Add everything together, which becomes so it means that if you want to represent everything as a single point, it's going to be almost 0.4 meter away from the bottom. Okay, and the moment of inertia is this number, so it's going to be then you can start to use this specific property to do angular velocity, angular moment, and anything you want to deal with the rotational movement using this number and this distance. That's how we proceed this kind of problem. Is there a question?